Hey everyone, welcome to Insights by Rish. Today we are going to implement a linear regression project of car price prediction. For that we have this particular dataset downloaded from Kaggle where we have the brand name of the car, the model, year in which it was bought, fuel type, transmission, owner type. This is actually we are going to predict the car price for the second hand car. That's not a new car. We want to predict that how many owners it initially had, and depending upon that the price varies. We have the engine power, the number of seats, and the target feature, which is price. This is what we want to predict. This particular dataset is downloaded from Kaggle, and I will provide the link for dataset in the description box. Do check that. Now beginning with now we'll start by importing all the necessary libraries that we require. So we'll import Pandas as PD. Then we will also import Seaborn if in case we want to do any exploratory data analysis. So Seaborn as SNS, and we also don't want any warnings here, so we'll say import warnings dot filter warnings, and we'll ignore. After this we will import the dataset. So I will import the dataset in the cardf pd.readcsv. Here I will provide the link on which my dataset is downloaded. Let's run this and let us try to display the first 5 rows of the dataset using the head method. This is the dataset that we have. The first thing that we will say, we will remove the unwanted columns here. As the car ID, we don't require the car ID to make any kind of predictions. That's mere index assigned to every instance. So we'll just drop the unwanted columns, and apart from that every column is necessary to us. So we'll just drop the car ID column. We will say cardf dot drop columns is equal to the column then that we don't require is car ID. We'll just copy it from here, and we'll provide in place is equal to true as we want to make our changes permanent. Now let us again try to display the first 5 rows of the data frame, and now you can see we don't have the car ID column. Now the next thing that we will do here, as we are in the process of data cleaning, we will check whether it consists of any null values. So we'll say cardf dot isna dot sum. So we don't have any null values here. Which is a good case, and we'll check the dimension of the data frame. So cardf dot shape. The data frame consists of just 100 rows and 12 columns. Now the next thing we'll start by converting the categorical values into the numerical ones. As you know, the machine learning model cannot handle any categorical values. It requires all the data in a numerical format, and hence we need to convert the data into the numeric one. Depending upon how many categories a column has, we choose what method to implement in order to convert the categorical values into the numeric ones. We'll start by converting the brand column. So let us check what are the unique values from the brand column. So cardf dot brand dot unique. So these are the few unique values from the car. So these are the unique values from the brand, and as we are having many multiple categorical values here, we will use one hot encoder in this particular case. So what we will do, we will say we will create actually a new data frame of brand df, and we will say here that pd dot get dummies. We will pass the column here which is brand, and let us try to check the first 5 rows of the dataset. Now they are in the format of true and false. This is because we haven't explicitly converted the data type into the integer. So for that we just need to say as type is int, and now you can see you have got all your categories into the form of numerical, the 0-1 combinations. So this was the one hot encoding that we did, and later we will just concatenate this particular column with the original data set. The next thing that we will do here, we will just check how many unique model names we have. So we'll say cardf dot, the column is model, model dot unique. And there are many unique model names here. So one thing that we can do here, either we can create one hot encoded data frame for all of this, or either you can just eliminate that particular column. But as we are having very few rows here, it will be very difficult if we delete this column for our model to learn. So we will just include this column. We will create a new data frame here of model underscore df, and we will just do the same thing what we did here. We'll just change the column name from brand to model. Let's run this and let us try to display the first 5 rows of our model data frame. Now you can see you are having 58 columns here. So when you are actually concatenating all these columns, it would be a very huge data frame. It will have multiple dimensions. So if we want, we can also perform some dimensionality reduction here later. Now the next column that we have here, next categorical column actually, is the fuel type. Let us check what unique values we have in fuel type. So we'll say cardf dot, the column name is fuel type and unique. Now in fuel type we just have petrol and diesel, so we don't need to perform one hot encoding here. We will just use the replace function. So we'll say cardf dot fuel type dot replace. We will replace the petrol with 0 and diesel with 1. So we'll say petrol with 0 and diesel with 1, and we will say in place is equal to 2 in order to make the changes permanent. Let us try to display the unique values from the cardf of fuel type column now. Now you can see the values consist of the fuel type consists of zeros and ones. The next categorical feature that we have here is the transmission. Again, we will check the unique values for transmission. So we'll say cardf dot transmission dot unique. Again, we just have 2 categorical values here, so we will perform the replace method here. We'll just copy it and we will change the column name from fuel type to transmission, and we want to actually replace manual with 0 and automatic with 1. After this, we'll again check for the unique values from the transmission column, and now you have the unique values as zeros and ones. So we have also converted the transmission column into the numeric one. The next categorical column that we have here after manual is the owner type. Let us check for the unique values from owner type. So we'll say cardf dot owner type dot unique, and we have 3 unique values here, first, second and third. Again, we can use the replace method here. So let me just copy this particular code snippet, and we'll change the column type from transmission to owner type. We'll say if the owner is first, it would be 0, it would be labeled as 0. If it's a second, then it would be labeled as 1, and if the owner is third, then we will say it as 2. Let's run this and let us now again check the unique values from owner type. Now we have 0, 1 and 2. The next categorical column that we have here after the owner type is, so we don't have any more categorical columns here. We are done with everything. Let us try to display our cardf dot head, and as you can see, we have converted all the categorical columns into the numeric ones. Now we just have this brand and model columns to be included into this particular data set. So what we will do, we will actually drop the original brand and model columns, and we will concatenate this particular data set with the model df and the brand df. So first we'll drop the unwanted columns. So cardf dot drop columns is equal to brand and model. And the next is model. We'll also say in place is equal to true. Now let us try to display the data frame. As you can see, we don't have that brand and model column here. Next, we will just concatenate here. We will name it as data frame df, and we will perform concatenation here. The columns that we want to concatenate here are the initial column is car df, then the brand df, and then the model df. And we also need to provide the axis here, the basis on which we want to concatenate. If axis is equal to 0, then we are concatenating on the basis of rows, and if the axis is 1, then we are concatenating on the basis of column. So here, as we are concatenating on the basis of column, we will say axis is equal to 1. Now let us try to display the first 5 rows of the df, and now you can see we have in total 79 columns, as we have concatenated the brand and model columns as well. So we have all the data now in the numeric way. The next thing that we will say, we will divide this data into the input features and the target features, so that we can perform data normalization on the input columns. So we'll say x is the variable, or you can say the data frame into which we are going to store our input features. So we want to include every column from the df except for the price column. So we'll just drop that particular column here. So we'll say df dot drop columns is equal to price. Let's run this and let us try to display. Now you can see now it has 78 columns, so we have included every column into our input feature except for the target feature price, and we will include that target into the y variable, which will be of series data structure df price. If you try to display the y, you will see the prices are in the format of series data structure. Now that we are done with dividing our data set into the input features and the target feature, next thing we want to do, we will perform the data normalization on the input feature. As you can see, if you try to do x dot describe, when you take the look at the statistical analysis, you can say that your every column is on a different scale. Every column is having a different minimum value and a different maximum value. We need to bring all this data on a single common scale using the min-max scaling data normalization technique. So we'll say from Scikit-Learn dot preprocessing, we will import min-max scaler, and we'll create an object of min-max scaler, which is a scaler. And then we will directly use the fit transform method here. You can also do both the things separately. First you can fit it and then you can transform the data, but in order to reduce the time, we will do it in one single go. So scalar dot fit underscore transform will transform your x data frame. Now if you try to display the first 5 rows of your x, you can see now they are between 0 to 1. Every column from the x data frame is scaled now. Next thing that we can do here after doing these things are there are many dimensions here. As you can see, there are 78 columns into this particular data set. In order to reduce the dimensions, we can perform the principal component analysis onto this particular data set. So we'll say from Scikit-Learn dot decomposition, you will import PCA and you will create an object of PCA. Here you want to provide that how many important data that you want to extract. So let's say I want to extract 95% of important data, so 0.95, and then you will say x underscore PCA is equal to, you will directly use the fit transform method here. So fit underscore transform x. Let's run this, and now you will have the value stored into your PCA in the form of array and not in the form of data frame. You need to explicitly create a data frame out of this. So let us just try to check only the first array, and you can see you are having now this many number of columns. You don't know exactly how many number. So we'll create a data frame for this, and if you want to check how many columns you have here, you will say xpca dot shape at 1. You are having total 45 columns here now. So you can see your dimensions are reduced from 78 columns to 45 columns. Now we will create a data frame out of this. We will say x underscore df is equal to pd dot data frame, and you will pass your data frame here as xpca, and you will pass the value here xpca. Next you need to create the columns. using, we will create it using the list comprehension, of course. So we'll say TC at I for I in range. You can provide the range. Let us store this. This is the range that we want to provide here. So we'll store this into some variable num, and we'll say for range in num. Let's run this, and we need to provide something like this. Let us try to display the first 5 rows of the XDF. Now you can see you are having 45 new columns. You will of course have 100 rows. So you have reduced your dimensions. Initially you had 78 dimensions, and from that we have reduced that number to 45 dimensions. You have extracted just the 95% of important data from the initial data set. Now you can perform train test split here. So we'll say from Scikit-Learn dot model selection, you will import train test split, and you will say xtrain comma xtest comma ytrain comma ytest, and you will pass train test split here. You will pass your new data frame, which is x underscore df, and the target feature, which is stored in y. Then the test size is equal to 0.2, which means 80% data in the training set and 20% in the testing set. And then the random state is equal to 42. Let's run this. And if you want to check now how many instances are included in the training set, you can say xtrain.shape and xtest.shape. So now out of 100, you have 80 rows in your training set and 20 rows in your testing set, and you have 45 columns. Next, we'll perform linear regression onto this. So we'll say from Scikit-Learn dot linear model, you import linear regression, and you will create a model is equal to linear regression, and you will say model dot fit xtrain and ytrain. Let's run this. And now that you have fitted your model, you can make some predictions, or you can also evaluate your model. So let us say you want to check the first true labels for the testing set. So let us check what are the first true labels for the testing set. So first 5 true prices are 16 lakh, 7 lakh, 13 lakh, 16 lakh, and 8 lakh 50,000. So the first 5 true prices, and let's see what our model has predicted. So let us say that pred is equal to, we are storing our predicted values in the pred variable, model.predict for x test, and we'll again display the first 5 predicted values. So as you can see, for 16 lakh, it has predicted 6 lakh 21,000. For 7 lakh, it has predicted 6 lakh 84,000. For 13 lakh, it has predicted 13 lakh, just the difference of point, just a difference of later terms here. And so you can see the predictions are approximate, and the predictions are very near to the original values. Next, we will evaluate our model. Now unlike classification algorithms where you have accuracy, you have classification report and confusion matrix, here in the linear regression you have some different evaluation metrics. You have mean test score, mean squared error, you have mean squared error, mean absolute error, root mean squared error. So we will evaluate it. So from Scikit-Learn dot metrics, you import mean absolute error and mean squared error. So mean squared error, and let us try to display mean absolute error. We'll pass the true labels which are stored in ytest and the predicted labels which are stored in pred. So this is our mean test, this is our mean absolute, so this is our mean absolute error. If you want to display the mean squared error, you can do so. You will say mean squared error. This is your mean squared error, which of course would be very large because you are actually taking the square of every term here. And you can basically use the best evaluation metric in the linear regression here, which is root mean squared error, and for that you require numpy. Import numpy as np, and you will say np dot square root of mean squared error. So this is your root mean squared error, which is of 5 lakh 2,379. If you want to, your ultimate goal is to reduce this root mean square error, and you can try it using different regularization techniques. You can use lasso regression or ridge regression. Let us try using the lasso regression first. So the first regularization technique is lasso regression. So from Scikit-Learn dot linear model, you will import lasso, and you will say lasso regression, or you can say lasso model is equal to lasso. Now here we will provide some hyperparameters like alpha is equal to 50. The max iterations that you want here are 100 and the tolerance level as 0.1. And now you will say lasso model dot fit x train and y train. Let's run this. The error is actually it's fit. Now you can again evaluate your model using the new model that you have created, lasso model. So instead of, you will say you will store the predictions of lasso model in the lasso pred variable. So you will say model dot predict for x test, actually the lasso model. And now you will just compute the same thing using the lasso pred variable. I think it's lasso. So we'll pass the y test and the lasso pred. Now you can see initially you had the root mean squared error of 5,02,379, and now you have it of 2,36,000. So you have reduced your error from 5 lakh to 2 lakh. But again, we will again try using the ridge regression as well. So we'll say from Scikit-Learn dot linear model, you will import ridge, you will import ridge, and you will create a model for this. So we'll say ridge underscore model is equal to ridge, and you will pass some hyperparameters here as well. So you will say alpha is equal to 50, max iterations is equal to 100, and the tolerance is 0.1. We'll again say ridge model dot fit your x train and y train. Now we'll store the predictions using the ridge model in the ridge pred variable, ridge pred, and we'll say ridge model dot predict for x test. Now we'll compute the same thing, root mean squared error, using the ridge pred variable. So you, instead of lasso pred, you will say ridge pred. Let's check this. And after using the ridge model, the ridge regularization, your error increased from 5 lakh to 7 lakh. So you won't be using the ridge regression here. The appropriate regularization technique here is the lasso regularization, the lasso regression, which reduced your error from 5 lakh to 2 lakh. So that's it for the car price prediction project. Thanks for watching.